Hey guys, so today we are going to be talking about absolute maximums and minimums, also known as absolute extrema. This is section 4.1 in your textbook if you wish to follow along in your book. Okay, so let's just get straight to it. So, we say that a function f has a relative maximum or a local maximum at a point C in its domain if the function evaluated at that point is greater than or equal to the function evaluated all the other x relatively near C. Now, if you like precise descriptions, then you're really going to hate this definition. Because what do we mean when we say near? Well, we mean if you go a little bit to the right or a little bit to the left, every function value is less than f of c. So basically, if you look at a graph of a function, it's any bump that goes upwards. And if we're going to have a relative maximum, then it makes sense that we have a relative minimum or a local minimum. We say that a function f has a relative minimum at a point C in its domain if the function evaluated at that point C is less than or equal to f evaluated at all other x near C. So think about a small dip in the function where it kind of goes down, bottoms out, and it comes right back up. Now, it might not be the lowest that function ever gets, but in that local area, it is the minimum. Now, this might be kind of hard to see without pictures, so let's look at an example function. Consider this situation, where we have this unknown function. We don't know what the equation is. We don't need to in this case. We just have the graph, and we've been tasked with finding the relative maximums. So the relative maximums are everywhere you see the function kind of go up and come right back down. So if you look over here, this left bump right here, kind of go up, peak, and we drop right back down. And we look over here between 0 and -5, we have another little bump. Between 0 and 5, we have another bump. Between 5 and 10, we have a bump at this upper arch right here. So just to point those out, at those black dots, that's where all the relative maximums are. Now notice the two little bumps there in between -5 and 5. They aren't near as tall as those two big towers on the left and right. But if you look at all the points around those two inner points, they are all less than or equal to it. So if you look at this point between 0 and -5, all of the values a little to the left of it and a little to the right of it are smaller than it. And the same thing for this one. So while there are points that are bigger than it, in this relative area, it is the maximum, hence the name, relative maximum. So essentially, when you're finding relative maximums, find everywhere you have kind of a point. You have a point there, you have a relative maximum there. Now let's repeat the process with minimums. And so let's find all the relative minimums. Well, if we look down here, we have a relative minimum down here, another one down here, and then at the points -5 and 5, we have two more relative minimums. And then at the point 0, the origin, it looks like we have another relative minimum. Essentially, all of the relative minimums are the points where that function dips. So it dips down and it comes right back up. That's what we call a relative minimum, where in its near area, it is the minimum point. So think about relative low points in your terrain. So imagine you're in South Plains, Texas, where we've got the big canyon up there. What's that called? Palo Duro Canyon. That is really deep in there. It really is. It gets very deep inside that canyon. It's like the second biggest canyon in the country. But it's actually less deep than the largest canyon in the country, which is the Grand Canyon. The Grand Canyon goes much deeper than Palo Duro. But Palo Duro goes the lowest than any other point in the relative vicinity. So Palo Duro would be a relative minimum in terms of depth. You do same things with relative maximums. If you go out into a small podunk town and who knows where, you might find a church steeple that's probably going to be the highest point in that town. But let's face it, there are a lot higher points on this earth. So that's kind of the difference between a relative and an absolute maximum or minimum. Relative just means it's the biggest or the smallest in its little area. All right, now that we have covered that, let's look at absolute maximum and minimum. So f has an absolute maximum at c if f of c is greater than or equal to f of x for all x in the domain of f. So what this is saying is f has an absolute maximum at this point if f of value at that point is bigger than every single other point inside the domain. So the absolute tallest peak. We do the same thing with the minimum. F has an absolute minimum at a point C if f of c is less than or equal to f of x for all x in the domain of f. So these definitions are similar to the relative maximum minimums, except these are the absolutes. There is nothing bigger than it, and there is nothing smaller than it. So that's the absolute maximum minimum. But let's look at an example of it. At this function, f of x is equal to sine of x, a function we should all know very well by now. If you look at this point right here, pi over 2 comma 1, right here, this is the absolute maximum of this function. Sine of x does not get bigger than 1. It does not get to 1.1. It does not get to 1.5. Sine is bounded above by 1. So at this point right here, we have an absolute maximum. Now, sine is periodic. There are other values where sine of x is equal to 1. Look over here. So add 2 pi to it. It hits it again. But the absolute maximum is not necessarily at a unique point. The absolute maximum, that value 1, is unique. It is the maximum. But there might be several points in the domain where the function achieves it. So it is the tallest point, but it can hit it a couple times. But it's still the absolute maximum. And then we can repeat the exact same process for the minimum. For example, on sine of x, we got one right here, 3 pi over 2 comma negative 1. Sine of x does not get smaller than negative 1. It doesn't get to negative 2, doesn't get to negative 10, doesn't get to negative 1.1, doesn't matter. It is bounded below by negative 1. Now, there's an infinite number of points where sine of x is equal to negative 1, but that doesn't matter because it never gets smaller than negative 1. And that's what's important. The value of the actual maximum and the absolute minimum are unique, but it might achieve those points in several instances. Okay? Now here I'd like to distinguish between absolute maximum, absolute minimums, and the points where they achieve them. The absolute maximum for sine of x is 1. The absolute maximum of sine of x is not pi over 2. Pi over 2 is where the absolute maximum occurs. It's a point, pi over 2 comma 1. But pi over 2 is not the absolute maximum. It's just where it occurs. And we can say the same thing with the absolute minimum. In this case, the absolute minimum is not 3 pi over 2. 3 pi over 2 is where the absolute minimum occurs. The actual absolute minimum is negative 1. So be careful, depending on what you're asked, you might be asked to give two different information. For example, if you're asked, where is the absolute maximum or minimum, that's when you say pi over 2 or 3 pi over 2. But if you're asked, what is the absolute maximum, then that's when you would say 1. If you're asked, what is the absolute minimum, that's when you would say negative 1. Make sense? That's right. You guys aren't here to answer that question. If that doesn't make any sense, shoot me an email saying, hey, I didn't understand that, and we'll see if we can work something out. All right. So that's it for absolute maximum minimums. Now, it's kind of fine and dandy to know about absolute maximum minimums, but we're going to take a step back and we're going to define something else. Okay, apparently we're going to talk about this first. My bad. So we have to ask ourselves this question before we get to those other definitions. What do you notice about the absolute maximum and the absolute minimum? For example, what do they have in common? So if we look at it, where it reaches this peak right here, or it bottoms out right here, what do they have in common? Now, one's way up here, one way down here, one's over here, one's over here. So location is really not what they have in common, but they have a same geometric aspect to it. The function levels out. It gets up here and it stops increasing and it starts decreasing. And down here at the minimum, it's decreasing, it's decreasing, it's decreasing, then it stops and then it increases again. So essentially, the function stops increasing or decreasing at these points. An absolute maximum, the function is no longer increasing here. Because if you were at this point and you were still increasing, well, then you're not at the maximum. There's a point bigger than it. So at this point, the function has stopped increasing. We've reached that maximum. The same thing about this minimum. The rate of change is equal to 0. It is not going anywhere. It is bottomed out. And I was being very specific when I asked about that question, about it is kind of bottomed out, where it's the rate of change is equal to 0. What does it mean for a function to have a rate of change equal to 0? Well, that means its slope at these points is equal to 0. The derivative at these points are equal to 0. And what does it mean if a function has a derivative equal to 0? Well, what is the derivative? It is the slope of the tangent line at that point. And then what is a slope, or what is a line that has a slope of equal to 0? That just means it is a flat line. It is a horizontal line. This is what I'm talking about right here. At the absolute maximum and the absolute minimum, it has a horizontal tangent line. Now, that's kind of an interesting, little factoid right there. That when we hit an absolute maximum or an absolute minimum, the tangent line, or the slope of the tangent line, is equal to 0. Or the tangent line itself is a horizontal line. It hits a barrier. It just runs into it, smack right there, and it decreases again. And then at the minimum, it runs smack into that tangent line and increases again. Now, this is an interesting phenomenon. Now, this is what we're going to study for the next few sections, actually. This idea of tangent lines and what does that tell us about the function. But before we go into more detail about that, we have another definition that we need to go over. Critical points. Okay, so critical points. What is a critical point? Now, if the derivative of f at a point x is equal to 0, or if the derivative at that point does not exist, then we call x a critical point. So, point x is a okay, I apologize if you can hear my dog barking. He is losing his mind at something. I'll go check on him in a minute. Okay, so, what was I saying? All right, so, to be a critical point, that means the derivative is equal to 0, or the derivative does not exist. Or, to put it in the context of tangent lines, for x to be a critical point, then that means the tangent line at that point is either horizontal or it does not exist. That's the two options for it to be a critical point. But what does it mean for it not to exist? Well, that usually means in this context that we have some kind of division by 0 when we take the derivative. The limits coming from the directions don't exist. Basically, where either we have a horizontal tangent line or one where we don't even know how to define the tangent line. And at that point, that is what we call a critical point. Now, I might be asking, why on earth would this be a critical point? Well, the naming for these things comes from the following theorem. The extreme value theorem. Now, you've heard me give this speech once, maybe twice, maybe 5, 12 times, but I'm going to do it again just because I can't help myself now. This is called the extreme value theorem. So, again, if something's a proposition, it's pretty important. If something's a theorem, it's very important. If it's a theorem that's so important that they named it after the guy who discovered it, that's really important. Now, let's suppose we have a theorem that they deemed was so powerful and so useful they felt that no one should ever have their name tied to it. It is too important. It needs its own name, such as extreme value theorem. Then that means it's going to be extremely important. All right. Now that I've talked about that for a second, because I just can't help myself. Okay. Man, it's really hard not to go on tangents when I do these things. It's really not. I know it's a waste of time. You're sitting at home doing something. Okay, I need to stop myself. All right, extreme value theorem. Here we go. If a function f is continuous, told you that was important, on a closed interval a to b, then the function f has an absolute maximum and an absolute minimum on the interval. Additionally, they can only occur at critical points or at the endpoints a and b. All right, let's break down what this means. So first off, let's start with the situation. We have to have a function f that is continuous. That really is an important condition. On some closed interval a comma b. That closed part's important. We need the endpoints to be included. So it has to be a closed interval. And then if we just have those two things, so really if you think about it, it's really just one condition. You require your function to be continuous. That's pretty much it. The closed interval is because we like the endpoints to be included. But so really with that minimal requirements, then we get the following. Then that means f has an absolute maximum and an absolute minimum on that interval. Now what does that mean? Well, that means if we have this continuous function on some closed interval, that means it can only get so high and then it can only get so low. It cannot take off to plus infinity. It cannot go to minus infinity. It has an upper and lower bound. It's bounded. It cannot go anywhere. It's stuck. Kind of like sine of x. Sine of x is stuck between -1 and 1. And now if you imagine any other function, just try and come up with a counterexample. Draw a function that is continuous on a closed interval, and then see if it doesn't have a maximum or an absolute minimum. I promise you will not be able to come up with something else. That's the neat thing about theorems. They're absolutely true. So, then the final point of this theorem, the part that makes it very useful, not just kind of cool, not kind of, it's kind of interesting. The part that makes this useful is that not only does it tell us that these things exist, it tells us where we can find them. These absolute maximums, these absolute minimums can only occur at critical points or at the endpoints A and B. So the biggest a function can get, or the smallest a function can get on a closed interval is at each endpoint or at the critical points. So where we have a horizontal tangent line or a tangent line that doesn't even exist. Now, you might be asking yourself, why is that true? Well, let's go back to that original function that we looked at, and let's take this theory we have developed and apply it to this. We look at the tangent lines at all of the relative maximum minimums. You can see that at these relative maximums and these relative minimums, they have horizontal tangent lines. They top out. They get there, they stop, and they come back. That's when you know you have a relative maximum or minimum, or an absolute maximum or minimum. We have these horizontal tangent lines. That is where we have our maximums occur. When the derivative is equal to 0. And when the derivative is equal to 0 at that point, we call these points critical points. So imagine if it occurred at a place that didn't have a 0 derivative. So let's say the derivative at that point was 2. Well, that would mean at that point, you're going to go up just a little bit more. You can go up just a little bit more. But even though it's only a little bit, you have found a new maximum, and it's a contradiction. You did not originally have the absolute maximum. So what the extreme value theorem is telling us that on some closed interval, so for example here you cut it off at -10 to 10, there's going to be an absolute maximum, there's going to be an absolute minimum, and these will only occur at the endpoints or where the derivative does not exist, or in this case, where the derivative is equal to 0. So that's what the extreme value theorem tells us. To find these absolute maximums, we can just look for where the tangent line is flat, where the tangent line doesn't exist, or the endpoints. So imagine if you didn't have this picture to look at, and all you had was some interval -10 to 10, and you were told to find the absolute maximum. Well, rather than checking every single point in there, all we have to do is take the derivative, figure out where it's equal to 0, figure out where it doesn't exist, and then we just check those points along with the endpoints. So, at most, 10 things to check. 10 things to check is a lot less than an infinite number of things between -10 and 10. Saves us a whole lot of time and effort. And we can't just do this for just relative maximums. We can also do this for relative minimums. The same principle. If we look at these relative minimums and these relative maximums, or these relative minimums and these absolute minimums, at all these points, they have a flat tangent line. The derivative of all these points is equal to 0. So if we want to find these relative minimums, just figure out whether the derivative is equal to 0 or it doesn't exist, and then check those points. And then the endpoints, of course. Now, That sounds like a whole lot of work, especially when you're looking at this graph. Because when you're looking at a graph, just eyeball it. But what if you don't have a graph? What if you're in this situation where we are just given a function f of x and we are told to find the absolute maximum and the absolute minimum? Consider this example. Given the function f of x is equal to the square root of 9 minus x squared on the interval -1 to 2. And we've been tasked with finding the absolute maximum and the absolute minimum of this function on the interval -1 to 2. All right, well, we know that we need to check the critical points and the endpoints. But right now, we don't need to worry about the endpoints. First thing we have to do is find the critical points. And to find the critical points, we need the derivative. So we have our function f of x is equal to the square root of 9 minus x squared. And since you guys are probably pretty good at taking derivatives at this point, I'm going to jump straight to giving the derivative, where in this case, the derivative is equal to -2x divided by 2 times the square root of 9 minus x squared. Don't believe me? Check that for yourself. In fact, it'd be a good exercise for you to just go ahead and stop the video right now and double check that that is in fact the derivative of our function. Okay, so assuming you paused the video and checked it, now we can move on. Now we need to ask ourselves the following question. When is this derivative equal to 0? Because remember, critical points occur at 2 places, where the derivative is equal to 0 or the derivative does not exist. First thing we're going to check, where is the derivative equal to 0? Okay. To do that, set the derivative equal to 0, and then we're going to solve for x. All right? So we have this fraction is equal to 0. But when is a fraction equal to 0? When the numerator is equal to 0. So we're really just asking, when is -2x equal to 0? Well, that only occurs at x is equal to 0. Simple enough, right? But now, when does the derivative not exist? Well, we have a fraction. The derivative is a fraction. It's -2x divided by 2 times the square root of 9 minus x squared. Well, we have a square root down there. We might have a problem with that square root being to try and take the square root of a negative number. But recall, at the beginning of this, we defined our domain to be -1 to 2. Now, -1 to 2, the square root is defined everywhere. We never have the square root of a negative number problem. So right now, we don't need to worry about that square root. The only problem we need to worry about is a division by 0, because that's what breaks a fraction, when you have a 0 in the denominator. So what we need to do is solve for when the denominator is equal to 0. But when is the denominator equal to 0? When 9 minus x squared is equal to 0. Because when 9 minus x squared is equal to 0, you have 2 times the square root of 0, which is 0, and we have a division by 0, and then so that's when the derivative does not exist. So really we just have to check when is x squared equal to 9, but what values make x squared equal to 9? Plus or minus 3. So now we have 3 critical points for this function at x is equal to 0, x is equal to 3, and x is equal to -3. How did we find those? Well, we took the derivative, we set it equal to 0, and then we determined where did the derivative not exist. That gave us all of our critical points. But now we have our critical points, we need to actually go find the absolute maximum and the absolute minimum on this interval. But we only care about the interval -1 to 2. So these critical points, 3 and -3, we don't care about them. They do not exist on our interval. So the only critical point we care about on this interval is x is equal to 0. It's the only one we care about. And what the extreme value theorem tells us is, to find the absolute maximum and minimum, we only need to check -1, 0, and 2. Because the extreme value theorem tells us that the absolute maximum and the absolute minimum only occur at critical points or endpoints on a closed interval. We have the closed interval -1 to 2, so we have to check x is equal to -1 and x is equal to 2. But we also have to check critical points in the interval, and the only one of those in the interval is x is equal to 0. So if you take back and think about this, We were tasked with finding the absolute maximum and minimum of this function on the interval -1 to 2. Think about how many numbers are in between -1 and 2. It's more than just 0 and 1. It's -0.999, -0.99999. Do that forever, and then -9.8, -9.888, and do that forever. And you're already getting bored of me trying to list off these numbers. So imagine having to go through and check every single one of those numbers to find the absolute maximum or minimum. That's ridiculous. So the extreme value took all of those numbers and it narrowed down our search to 3. So we went from a ridiculous number of numbers to 3. That's really no problem for us to check. And how do we check these values? Well, personally, I prefer a table. Take your values, put them in a table, check f at each point, and then for the absolute maximum, pick the biggest number. For the absolute minimum, take the smallest number. It's as simple as that. So we have our table. The first number we're going to check is x is equal to -1. So take -1, plug it into f, and we get f of -1 is equal to 2.828. Repeat the process for x is equal to 0, and we get f of 0 is equal to 3. Why is it equal to 3 and not -3? Because f is a function, and each function can only have one output for each input. And we're dealing with the square root function, well, we always assume it's going to be the positive number. So f of 0 is equal to 3, and then we need to evaluate f of 2, and f of 2 is equal to 2.236. So using this information, we can determine the absolute maximum is 3, and it occurs at x is equal to 0, and the absolute minimum is 2.236, and it occurs at x is equal to 2. So we took our critical points that are in the interval, we took our endpoints. We know from the extreme value theorem these are the only points we have to check. We plug in these 3 values into the function. The biggest number on this right column is our absolute maximum. The smallest number in this column is our absolute minimum. And once again, I'd like to point out that I did not say the absolute maximum was 0. That's where the absolute maximum occurs, but it's not the absolute maximum. The absolute maximum is 3. Same thing with the absolute minimum. The absolute minimum is not 2. It's 2.236. X is equal to 2 is where the absolute minimum occurs. All right, I think that's where I'm going to wrap it up for this video. This is going to be part 1 of section 4.1. Make sure you watch the part 2 of section 4.1, where we are just going to go over examples about using the extreme value theorem to find absolute maximums and absolute minimums. And I strongly suggest watching that video because these techniques, these idea of finding critical points and checking them, they're not going anywhere. We're going to be using them for a good, probably the remainder of the semester. There might be one section where we don't use it, but for the remainder of the semester, we're going to be using this idea of critical points and determining absolute maximum and absolute minimums from them. All right? So I will see you in